In this video I am going to be showing you how you can implement a semantic search engine using .NET and ChatGPT, and the example will be oriented to a tax administration that is implementing this to answer questions from taxpayers. I will start by discussing the mechanisms we will use, then show you a demo of how this works, and at the end I will show you the actual source code. All of this material is open source, so you can find it in GitHub and the link is in the description below. The idea is to get the search engine to answer arbitrary questions, such as do I need to pay taxes if I am a student? And have a reasonable, accurate answer such as what you see in the screen now. I do not want to implement a chatbot, at least not for this example, although a chatbot would not be difficult to implement as an extension. I am interested in having a useful tool that answers questions and does it well enough to deploy it to the public website, and do this with a very small investment. A tax administration usually has a collection of documents that is known as a knowledge base, and most of the time going through these documents to answer a simple question is not realistic. Taxpayers don't have the time or expertise to do this. The idea is using these documents to implement something that the taxpayer can use to answer simple questions, in English, or any other language, and have the artificial intelligence engine reply with a simple and correct answer that the taxpayer can use. So, this is the architecture of the system I will demonstrate today. It's a very complicated figure, but stay with me. You will understand in a few minutes. In the left of the image, you see the knowledge base. Next to every document you see a list of numbers. These are called embeddings, and we will use these numbers to find those documents that may have the information we need to answer a question. Consider this analogy. Imagine that every word or phrase in a language is a point on a map. Embeddings essentially assign a set of coordinates to each word, placing them at specific locations on the map. Words with similar meanings or related concepts are placed closer together, while words with different meanings or unrelated concepts are placed further apart. For instance, in this hypothetical map, the phrases helicopter, slow car, and fast car would be positioned close together, as they share similar meanings. They are modes of transportation. Conversely, the phrases agile dog and tasty hot dog would be placed further apart, as they represent unrelated concepts. In reality, embeddings are points in a multidimensional space. Imagine that we are using embeddings in a three-dimensional space. Phrases are assigned a position on this space by a large language model, such as ChatGPT, such that the distance between related concepts is small, and the distance to unrelated concepts is large. In this example, the distance between yummy burger and delicious hamburger is smaller than the distance between yummy burger and tasty hot dog. Different types of burgers would naturally be grouped together. For embeddings, this is done in a multidimensional space that, in the case of ChatGPT, has more than 1,500 dimensions. My mind cannot possibly visualize this many dimensions, and it's hard to accept that this is sufficient to be able to index a document or phrase based on the concepts inside, but it works. So let's go back to our architecture slide. For every document in our knowledge base, we will calculate an embedding. When we have a question, such as what is the tax rate for VAT, we will calculate the embedding for the question. We can use these embeddings now to select those documents in our knowledge base that are most likely to have the answer to our question by simply calculating the distance from the question to the document in this multidimensional space and selecting the top two documents. Now we have two documents that may have the answer to the question. The magic trick is completed when we pass to ChatGPT these documents and the question, and we ask it to answer the question in the context of these two documents. ChatGPT, as a large language model, is really good at following instructions, reading documents, interpreting them and finding the answer to a question. And since we can ask it to be brief, it will simply say the VAT rate is 15%. Let's see how this works in practice. I will be using a fictitious tax administration for an imaginary country called Laurania. I will start by verifying that ChatGPT does not know about our tax administration, and indeed, it has no idea. It only knows that this is a fictitious country. For this example, I built a very simple knowledge manager specifically for our semantic search tool. This is a tool that I use to record small articles extracted from our larger knowledge base. Here, each article is limited to a single topic to improve the precision and relevance of search results. This helps the large language model understand the context and provide more accurate responses, since very large documents often cover multiple topics. Even though ChatGPT embeddings can encode approximately 16 single-spaced pages, I try to keep the articles small and focused, typically under 1,000 words. To show that our approach works, I will try to get the normal ChatGPT to answer a generic question about the Lorraine tax administration, such as what I can do if I have a dispute. ChatGPT gives me a generic answer that is not helpful at all. It is about a tax administration, but not about the Lorraine tax administration. Sadly, ChatGPT has no knowledge of the Lorraine tax administration and will not be able to answer any questions for our taxpayers. I can change that, using the search tool that I constructed using the architecture I showed earlier. This tool uses ChatGPT, but it provides it with the necessary context from the knowledge base using embeddings. When I ask it a question that is not directly in any document, but is related to some concept that is known, such as if I can benefit from being green, I will get a correct answer from the context of Lorraine. The tax administration does provide tax credits from being conscious about the environment. This is quite impressive. One nice feature is that in the right-hand side, I am displaying the list of documents that matched our embeddings with the corresponding similarity score. This way, the taxpayer can read the detailed knowledge base articles. If more information is required, I can ask similar questions using variations with regular English text, and the system will answer with similar correct information. The system will provide a match even if I ask a question that seems to be very broad, like tell me about carbon emissions. The link is very weak, but I still manage to get a relevant answer. I will go over a couple more examples, with questions that are in natural language such as those that would be used by any taxpayer, and the system is giving me relevant correct answers that are specific to the Lorraine tax administration. For example, let's ask what I can do if I have a dispute. Good. I now know that I can submit a request within 60 days. I wonder if there is anyone in the tax administration that could help me. Interesting to know that the tax administration has a tax advocate. Maybe I can use the system to find out how we can get in contact with this advocate. When I ask a question that does not seem to have an answer in our knowledge base, I will get a I do not know answer. This is good because it shows that ChatGPT will not make up stuff it does not know. Let's teach ChatGPT how to answer this question. I will add to the knowledge base an article that I found that has all the relevant information about how we can contact the taxpayer advocate. This article has a lot of information, including the physical address, email address, website, hours of operation and other relevant details. Somewhere in this article is the phone number. Now let's ask the question again. The system can answer now with the correct information. Adding a new article was easy. Let's ask another question that I know is not in our knowledge base. I would like to know the tax obligations of diplomats in Lorraine. The system does not know, so let's teach it all about the subject by adding the relevant article to the knowledge base. When I ask the system the question again, I obtain the current answer. I can now ask other question on the same subject, and ChatGPT will answer with the correct information, extracted from the article I provided. One final note is that I can even ask ChatGPT to be brief, rather than verbose, and the answer will be the same, but with less text. This is an impressive implementation that traditionally would have taken years of painstaking development, but I implemented it in a couple of days with minimal investment. Let's see how the system is implemented. Remember that you can download the entire exercise from GitHub and the link is in the description below. To use ChatGPT for our example, we need to use the Application Programming Interface, also known as API, that the company OpenAI publishes. This is available in the platform.openai.com webpage, where you will find a specific reference page for the Embeddings API. Note that to the right of the screen is the example request and the parameters we need to pass to the OpenAI system to use it. There is also a separate page for the Completions API. This is the second API we will be using to ask ChatGPT to interpret the knowledge base documents and find the answer to our question. You may want to go over these APIs in detail to understand how to use them and the most appropriate values for each of the parameters expected. Let's open the Visual Studio solution for our example. You will notice that the solution has 3 projects. The Semantic Search project is the user interface that allows us to search ChatGPT. The Knowledge Base Manager project is the user interface that allows to add, modify, or delete knowledge base articles. I will not go over these in detail since they are very simple. Rather, I will focus on the ChatGPT interface project, where all the magic happens. We are using Entity Framework within .NET to store all the relevant information to a SQL database. The knowledge record class stores all the information about the knowledge base article. This is a simple class that has a title, a content for the article, and the corresponding embedding vector. ChatGPT allows us to calculate embeddings only for about 4,000 tokens, so we include a field where we store the number of tokens that this article contains. An embedding vector is simple an array of numbers. If we look at the knowledge vector item class, we see that it is just a number, but we have a class defined for it so we can save it to the database. There is a class called Knowledge Record Manager where we have all the functions that allow us to create, modify and delete all knowledge base articles. Once we update the database for our system, we can see that the system creates a database called Semantic Search DB, and this database contains only 2 tables, one for the knowledge base articles and one for the embeddings vector. Let's look at what is stored inside the knowledge base table. We have the title, content, and number of tokens for each knowledge base article. The knowledge vector items table has only the corresponding embedding vector, where each row in the database has one number for this vector. Let's go back to our Visual Studio code. As I said before, the Knowledge Record Manager contains all the functions that allow us to maintain this database. The magic happens in the ChatGPT class. This class has only 2 public methods. One method calculates the embeddings for a particular knowledge base article, and one method obtains an answer from the ChatGPT system for any given question we may ask. Keep in mind that the Knowledge Base Manager calls the getEmbeddings function when it is saving a new record. Let's look at the implementation of this function. All we are really doing is creating an HTTP client that has the text of the article in the message payload, and the definition of the model that we want to use within the class of embeddings in OpenAI. This model is defined in the application configuration file. We can see in line 17 that we are using the text embedding ADA2 model. This is an efficient and cheap model that minimizes our operation cost. The API call will return a JSON object that we can deserialize into a numeric vector containing the 1536 dimensions. Let's look now at the source code for the function that takes a question and asks ChatGPT for a reasonable answer, given a context. Again, all we are really doing is creating an HTTP client that has the prompt we will pass to ChatGPT, and the definition of the model that we want to use within the completion engine in OpenAI. Like in the embeddings function, this model is defined in the application configuration file. The trick here is constructing the prompt. The prompt needs to give precise instructions, and these need to include the context and the question. Let's look at the function in line 246 called getPromptForQuestion. Constructing this prompt is what makes ChatGPT work. Let's look at an example of what a prompt looks like. The text in blue is the context, extracted from our knowledge base. The text in red is the question that we want an answer to. The text in black are the instructions provided to ChatGPT. If we submit this to ChatGPT, it will answer 60 days. Now back to the code, we see how we are constructing this prompt in lines 209 through 223. We need to get, from our database, the context by finding those knowledge articles that are similar, conceptually, to our question. We do this in the function called getContextForQuestion. All this function does is obtain from the database the knowledge base articles that have the greatest similarity score to our question, and then constructs a string with the contents of each article. The getSimilarityScore for question function is at the heart of this magic. In this function, two things are happening. The first is that we obtain the embedding vector for our question in line 92, and in line 93 we convert this vector of 1536 numbers into a comma-separated string. The second is that in line 118 we pass this vector to a stored procedure that will find knowledge base articles that are similar to the question. Let's look at the stored procedure that handles searching for conceptually similar articles. All that this procedure does is get a list of all articles in the database, and inside a cursor, for each article, obtain a similarity score. We typically use a mathematical function called cosine similarity, and you can see how we would determine this score in the commented code. Since ChatGPT embeddings normalize the result, the similarity score is given only by the dot product of the question vector and the knowledge article vector. This is a fast operation that is easy to compute. The stored procedure returns the top n results to the search function, that then displays the answer that ChatGPT gives us. This is pretty much the extent of the magic behind semantic search using ChatGPT. There is some syntactic sugar that is added to complete the cycle, and I encourage you to download the source code and try the system. Examine the code carefully and you will be amazed how simple it is to build a system that, before large language models existed, would have taken an army of programmers and a very long time to produce.